Now, entanglement is commonly defined as a group of particles where the quantum state of each particle cannot be defined independently. This already brings to mind the definition of a holon as an individual unit. Now, consider Tononi's definition of a complex in light of concepts like entanglement and relaxation time. By his definition, it would be impossible to know the interior states of a complex by observing its behavior. Because more information is passed internally, even among the narrowest choke point between internal subdivisions, than can be expressed externally, it's impossible to definitively deduce internal state via observing behavior. This suggests the entire complex is at least partially entangled from the perspective of an outside observer. Now, an internal means of recording aspects of its state would practically guarantee they would become available to the environment eventually, and memory is a very useful mechanism. But having a means of suspending such an internal measurement would allow the organism to make use of quantum effects in a neural context, as some organisms are already known to do, for example, during photosynthesis. Reference 9. Now, the clash between quantum and classical physics has the potential for so much cognitive dissonance that we tend to find various means and shortcuts for reconciling them, even at the cost of precision in our models. One of these is to naively separate types of systems by scale, and in this approach, systems at very low temperature and scales are modeled with quantum mechanics, with everything larger and warmer modeled as a classical system. Reference 10. This separation of responsibility works very well for making predictions, but the models remain stubbornly irreconcilable, and our intuitions about the world are often at odds with themselves. So, this investigation suggests that quantum mechanics are present at every level of organization, and have a factor of some relevance in any experiment. How well it reconciles our intuitions about the world at small cold scales and large warm ones is an indication of how well this article has done its job, in a sense. So when two particles are entangled, we might say that they're properly modeled as a single system and that their respective states can't be described independently. Although the two particles can each be thought of as separate, their behavior can only be understood when we take them both into account. So the concept of entanglement from physics corresponds directly with the philosophical concept of holons. Holon can only be thought of as a single thing. If you attempt to reduce it to its subcomponents, it causes a loss of information which decreases the accuracy of your prediction. So, if we apply the philosophical concept of holons, we can indicate when it's impossible to directly observe the interiority of a system, and therefore when quantum dynamics could be trickling up, as they do during photosynthesis. So any system which cannot be accurately modeled as the sum of its parts displays some behavior particular to its own level of organization. The inability to observe all components of such a system indicates the possibility that there's a significant quantum behavior somewhere in those components. So one approach that this study proposes is to take a gradated approach to this scaling problem rather than a sharp segregation of quantum and classical models. So which model is applied to a system is typically a question of what is most functional and is not always necessary to choose between alternatives as though it's a binary choice. So for example, in fluid dynamics, where there's a flow, which is whether a flow is turbulent, is determined by a non-dimensional parameter called the Reynolds number, and that's given by the definition R sub E equals rho, I believe that's a theta, rho theta L over mu. So where R sub E is the Reynolds number, rho is the fluid density, theta is the velocity of the fluid, L is the length of the airfoil or diameter of the pipe through which the fluid is interacting, and mu is the dynamic viscosity of the fluid. So fluid flow is generally considered laminar if the Reynolds number is below 2300, and transient or turbulent when it's above. And I always thought of turbulence as an objective measure, because if you have a dye stream or a smoke stream, a turbulent flow looks very different from a laminar one when you are observing it in the lab. And it was quite a paradigm shift to me when a mentor casually mentioned that the reference length L is arbitrary. So that refers to an entire wing of a plane or the wing's smallest adjustable flap if we want. A single flow could be both laminar and turbulent, depending entirely on the size of the object with which it's interacting, or the perspective of the object from which we are trying to determine whether there is a relevant turbulence or not. Turbulence is only a useful concept in relation to a specific solid body with which the flow is interacting. Perturbations that are turbulent to one object can be laminar to another. Now, Einstein's theory of relativity demonstrated that the relationship of the observer to what is being observed can influence how an experiment turns out, reference 11. Despite how widely Einstein's theory is accepted, many of us continue to habitually think in terms of a single truth, as though there's an unimpeachable observer who could provide a consistent answer to all questions about the state of the universe. And although this premise underpins much of classical physics, we don't accept it if we wish to form an intuitive understanding of how time really works, given the theory of relativity. If there were a single unimpeachable observer, the effects that only take place in the absence of an observer couldn't happen. Now, there's no obvious way for an experiment to distinguish whether the collapse of a wave function is an absolute fact caused by the observation, or whether the distinction between superposition and collapse only has meaning relative to an observer. If we think of entanglement as an absolute truth, it's slightly simpler, but something being true only relative to an observer is not so far outside of our daily experience as the turbulence of flow example shows. Momentum is another excellent example. It's commonly accepted that momentum is only a meaningful concept given an observer with its own momentum. And it might be helpful to take a similarly relativistic view of the wave function. Just like an intuitive identical fluid might appear laminar or turbulent depending on the pipe through which it flows, the best model for a system might be quantum or classical depending on the nature of our interaction with it. And a more useful approach may be to think of systems not as either entangled or classical, but as a density function similar to how we visualize quantum systems. Now, consider a density function which represents the possible states of a system. The more precise our observation of it, the more we can treat the density function as though it had a single value. But at no time does our measurement error change from non-zero to zero. Whether our uncertainty is relevant to our inquiry is an arbitrary choice. It depends how many significant digits we're trying to measure to. We first have to decide what we want to make predictions about and how accurate our predictions have to be. Then we can determine whether the uncertainty in the system is large enough to affect it. When we work at a quantum scale, the uncertainty is almost always relevant. At classical scales, it's typically always smaller. But that uncertainty is never eliminated as we change scale. There are scales where it can be safely ignored and scales where it can't. Whether a system is quantum or classical isn't a function of the system, but what we're measuring or observing about it. So McFadden and Al-Khalili represent a very interesting take on that so-called scaling problem in an article on adaptive mutation, reference 12. And they draw on Zorek's expression of the time scale over which quantum coherence is lost, reference 13, to present a possible explanation of how adaptive mutation can take place despite the low probability of a given adaptive mutation. So central to their model is the idea of relaxation time, how quickly the energy of a particle dissipates due to its interaction with the environment. The time it takes to go from superposition to fully observed is a reflection of that relaxation time. And this variable is also important to the quantum Zeno effect. If the relaxation time is relatively short, then if you want to demonstrate the quantum Zeno effect, you have to also observe very quickly. If it's got a longer relaxation time, then you only need to observe on a longer interval. Now, this concept may be important to the question of how quantum mechanics, which clearly determines the behavior of the smallest building blocks of our world, influences the world of our everyday experience. So, a marble rolling off a table and the moon orbiting the Earth produce radically different everyday phenomenon while obeying the same laws of gravity and inertia. In the same vein, we can expect the laws of quantum mechanics to be present at a scale the same way they're present at the scale of single atoms, without expecting the behavior to be identical. The variability of relaxation time with scale, and the necessarily partial nature of decoherence at larger scales gives a means of visualizing this transition more smoothly. So, as opposed to the hard transition between quantum, classical, and relativistic behavior we typically assume when we consider different scales of physics. Now, we tend to think of particles as being purely in superposition, and then decohering into a single classical position following an interaction. But again, if we talk about the particle changing, then that assumes there's a single infallible observer who keeps track of the true state of the particle, and that that observer somehow doesn't affect the true state of the particle the way our observing it does. So, in fact, each observer has a perspective, and what that observer measures can itself be in superposition from the perspective of another observer, reference 14. Consider a collection of particles, each with its own perspective. They're isolated, and therefore in superposition of various possible states. The higher the temperature of the collective system, the more likely any given pair of particles is to interact, which results in a shorter time to decoherence. We could also say the higher the temperature, the more quickly each particle's energy dissipates through the system as a whole. Now, McFadden and Al-Khalili asked how would this appear from the perspective of the particles, particularly a group of particles in a DNA chain. Now, suppose a proton is isolated and in superposition. It interacts with another protein, which causes both their wave functions to collapse. And we might prefer to conceptualize it, their interaction takes place in a particular way, which limits the possible future states either of them can display. Now consider a third, more distant proton, which has not interacted with either of the first two. Now from its perspective, both the first two protons are entangled and in superposition. When it eventually does interact with one of them, some of the information transmitted to it will relate to the history of these two particles' interactions. From a fourth proton's perspective, all three would have a probability density function that resolves into a particular position and possibly a particular history when they interact. The time required for a particle's energy to dissipate is essentially the time required for it to interact with its environment to such a degree that it leaves a signature in the ambient heat. So that's the relaxation time of a set of coherent particles, and it's a measure of how quickly the energy difference dissipates. And McFadden and Al-Khalili point out that a beneficial mutation would leave more of a signature than a random one, and they talk about that in the concept of evolution and how adaptive mutation could be more likely to happen or more likely to be observed than a random mutation. Now, consider this quantity in the context of the scaling function. Energy in a system behaves differently depending on scale. A system comprised of many particles is more likely to interact with a different system, but the exact state won't be determined as quickly. So to put it another way, a larger system takes longer to make a unique signature in its environment. It has a smaller surface area relative to its internal complexity. So the larger the system is, the easier it is to observe it partially. The harder it is to observe it completely. Much more data can be gathered immediately, but there's also more uncertainty behind what is initially obvious. So if we think of scaling in quantum mechanics as a function of energy dissipation, we can intuit how scaling changes the nature of quantum effects. The larger the system, the more likely there is to be a partial interaction, the less likely there is to be a complete interaction. And some internal entanglements are likely to remain in place even as some surface level interaction reduces the size of the possible state space. So this approach offers an intuitively satisfying means of scaling up bounded region theories of quantum mechanics, as people like Öko, Hameroff, and Penrose proposed. I'm not including Tononi in that because he doesn't really touch the physics of it. He talks about mathematics of networks in the brain. Now, it's important to remember in this context that the reduction in possible states happens from a perspective. So an interaction between a system and an observer reduces the system's possible states to the observer, while a third party that has no interaction with either system with either the system or the observer, perceives a closed system with different potential probability distribution and different interiority. Now, many scientific models treat the abstract heat bath in which a system resides as a sort of universal observer, and that can definitely be useful. It helps the math make sense. It may also be an accurate description of the universe in a fundamental sense, but we have to remember that as individuals making our own observations, that perspective isn't directly available to us. We can't read the heat bath, at least not through our five senses. When we speak of interaction, we typically refer to two holons, like an experiment and an investigator, interacting with one another. So interactions between a holon and the heat bath in which it exists is another matter. The universe might have access to a lot of information about the experiment via the heat bath, but only a small portion of that would be accessible to the investigator, and it wouldn't become available to the universe until quite a bit later. So those wave function collapse effects wouldn't happen on the same time scale from the interaction with the heat bath. Now, energy diffuses from a holon to the environment as a function of the surface area relative to volume. So a large complex holon, like a human, will always be in a state of partial diffusion. Some aspects of the holon will be observable to other holons, while other aspects will be purely internal over their duration, with only their tertiary effects ever being available to be perceived by outside observers. Holons are, in some ways, defined by their rate of exchanging information internally compared to the outside world. And if Tononi's model holds, which it's a really good model, then that internal interaction, that internal rate of information transfer, is also a measure of the consciousness that a system has. Now, there is still internal interaction in this model, of course. So McFadden and Al-Khalili, in their example, protons in a DNA molecule still jostle their neighbors, but precisely how this happens is better described as a probability distribution than through classical modeling, because again, the precise ways that this happens isn't necessarily available to the heat bath. Our classic view of time probably causes much of the trouble when we try to think intuitively about matters of quantum physics and scale. So we're accustomed to thinking of holons that extend through space as not being quite infinitely divisible. My arm is extended through space. It could be divided up, but it wouldn't be an arm, or at least it wouldn't be the same kind of arm as it is when it's not divided up and extended through space. And this is an aspect of what it means to be entangled. The subcomponents of an entangled system have some relation to one another. And if they were treated as separate and unentangled, then relevant data about the system would be lost. If my arm were subdivided, you would not be able to model it the way you model an arm that's attached to a human. And so in a quite literal sense, the entanglement of a system is synonymous with the system being a holon. And as experiments like the quantum eraser show, holons can also extend and be entangled through time. So our conventional way of thinking about time as infinitely divisible, much as we used to think about light, is probably incorrect. Systems can no more be infinitely divisible by location in time than by location in space. And we might say that we can specify spans of arbitrarily small division, but some quanta will extend beyond these boundaries, and we lose potentially important information if we try to divide up a holon without taking into account its own boundaries.